Welcome to the third Embedded Implementers Forum session, MicroTCA for Industrial Applications, Future Ready. I'm Brandon Lewis here with a panel of engineers who will present how MicroTCA platform technology, which has become really popular at high energy physics labs like CERN, is primed for use in markets like automation, communication, and pretty much everywhere else. Our panelists today are Heiko Korte, VP and Director of Sales and Marketing at NAT Europe, Thomas Holzapfel, Head of Sales at PowerBridge Computer, and Ivan Garcia, President and CEO of Ixos Technologies. You can find more background on the panelists in the presenter window, if you're viewing, which you can access in your viewing dashboard by simply clicking on their image and or title. So this session is going to consist of 15 or so minutes of presentation on MicroTCA and the sort of the state of the union. And after that, we're going to move into Q&A with the panelists. So you're going to want to participate in that. And to do so, use the Q&A tab, which is in the upper right of your webcast window. And we encourage you to make use of it early and often, even while they're still going through the presentation materials. If you have questions regarding the webcast operation itself, like your slides aren't advancing for some reason or you can't hear anything, submit those questions as well, and we'll have a technician assist you. And next to the Q&A tab, you'll note that there is a handouts tab where the presentation slides for today's session are located, so you can download them for your reference. Final note before we begin is that all Open Systems Media webcasts are copyrighted and may not be recorded without prior permission. So at this point, we can get started, and I think we're going to pass the talking stick over to Heiko. Let's see what Heiko has to say.
Hello, my name is Heiko Korte, and I am VP and Director Sales and Marketing with NAT. And I would welcome you to my presentation, MicroTCA and Next Generation, as part of the Open Systems Media panel discussion. Before starting to talk about the next generation with MicroTCA, we need to take a quick look at history in order to understand where MicroTCA came from. VME was one of the most successful embedded standards ever, and it was adopted in 1982. VME was extremely successful and accepted across almost any market, including the telecom market. Being a parallel bus architecture, however, it was not able to cope with the requirements telecom equipment manufacturers and public network operators had when mobile communication started. This was when the network equipment manufacturers and the mobile operators sat together and defined a standard which would provide exactly what they needed for their networks. And ATCA was born. 4 years later, MicroTCA came into existence. It has been derived from ATCA, and as it would reuse the advanced mezzanine cards, which have been defined as mezzanine cards with ATCA. With MicroTCA, those AMCs would be plugged onto the backplane directly. And MicroTCA was targeting at any telecom application ATCA would be an overkill for. So the fathers of MicroTCA had a clear vision on where MicroTCA would be used. Now, before starting further in the presentation, let me get the nomenclature right. So I'm using XTCA very often, which refers to ATCA and MicroTCA in the same way, because both standards share very much or a lot of things in common, and specifically the AMC cards as the binding and connecting part. So where is MicroTCA being used these days, apart from telecom and communication? Because we're thinking about the next generation, so there has to be a success story behind it. And it is. MicroTCA is used in almost any vertical market, be it traffic and transportation, machine control, automation, process control, and many more, just to give some examples here, where MicroTCA has paved its way because of its flexibility and its scalability, from very small to very enhanced systems with a lot of functionality there. So how is MicroTCA being used today? What you see now here are the figures that the fathers of MicroTCA were looking at when MicroTCA came into existence. So we were using basically 4 fabrics, gigabit Ethernet at 1 gigabit Ethernet, PCI Express by 4 up to 32 gigabit per second. We were using Ethernet, mainly XAUI, as a by 4 link given up to 10 gigabit per second, and of course here Rapid IO. Now, when we look at how MicroTCA is really used today, we can already see that MicroTCA had some enhancements here, specifically on PCI Express, where we are using by 8 links these days. And with Ethernet, we are already at 40 gigabit per second on the backplane as well. Now, when we look at what MicroTCA needs to deliver tomorrow, we have to understand that this demand on bandwidth is mainly coming from challenges imposed by the new processors, RISC CPUs, x86 CPUs, large FPGAs that contain a lot of I/O, and very often they also contain on-die processing capabilities in form of cores, processing cores, etc. And of course, fast I/O is also impacting the performance demand here. So that actually made a lot of people thinking that if we want to meet those challenges or those requirements, we would need to upgrade the spec. There are a couple of things that are limiting the devices as when they are designed as per the current spec in order to meet the challenges of the future. So PICMG, who owns MicroTCA, formed a new work group called Next Generation MicroTCA, and the members represent manufacturers and users from almost any area, be it hardware like chassis, electronics, and as well as mechanical components and semiconductors. So we have everyone on board who is contributing to the next generation in order to support us meeting those challenges. The work group is active since the end of 2019, and our goal is to keep MicroTCA alive for the next 10 to 15 years. Keeping in mind that MicroTCA has been adopted in 2007, we already kept our promise for the first decade, and now we're targeting to the next decade. And here, the primary goal, apart from keeping the spec alive, is of course keeping the next generation of MicroTCA backwards compatible, so that we create a clear migration path for our customers from where they are today and where they need to go to tomorrow. Currently, the the work group decided to update the base spec, MicroTCA 8.0, which has its current revision 2 to a intermediate revision 3 as an intermediate step for the final next generation spec. So we are enhancing power budgets and bandwidth. The draft version is currently under internal work group review, and the work group expects the specification to be released for review and vote by the PICMG executive members later this year. So with that being stated, I am at the end of my presentation, and I would like to thank you for your attention.
That's great. Now we're going to bring on Tomas Zapfel of PowerBridge. Tomas, take it away.
Yeah, thank you, Brandon. Yes, on behalf of myself, Thomas Holzapfel, working at PowerBridge Computer in Germany. Also welcome to the audience. I would like to give you a little bit more in-depth what MicroTCA, where MicroTCA nowadays is used already. Yes. So this is the application fields PowerBridge is working at. As you see, almost every aspect of embedded technology we are working at. So we found MicroTCA to be a very valid substitution for several deployed systems in the market, which has a couple of which were using a couple of industry PCs. Industry PCs are always difficult to maintain, and we utilize the fact that MicroTCA is capable to have up to 6 different root complexes in one system. So in fact, what you see here is a system, a MicroTCA system, which consists of ideally 2 independent PCs, which every PC is doing a dedicated task at a time. Both are connected internally via gigabit Ethernet, so they can share data and distribute data between each other. And this is very much utilized in test setup for GPS receivers for satellite communication. Another very accepted application in industrial automation is the control of a printing process. So in fact, in printing process, you have a lot of bandwidth you need to share. You need to record pictures, high resolution pictures, may it be visual or non-visual images, and you have to process these images in real time. This is basically something where MicroTCA really has made his fortune, in a way that we utilize the PCI Express links in the backplane, but we also utilize gigabit Ethernet or 10 gigabit Ethernet in the backplane to bring in all the different images being recorded from different cameras. In fact, the system you see there is used for banknote inspection. Another application, and that is primarily in the good old way MicroTCA originally was dedicated to. It was in IT communication, in telecommunication. So it's basically a MicroTCA system which takes all the emergency calls here in Germany, for instance. We have a central 116, 117 emergency number if you want to reach out for a doctor, and that is fed through a MicroTCA system. The interesting stuff was that the customer wanted to have a visual impression of his system to be not a MicroTCA system, but a dedicated system. So what we designed basically is a chassis. We turned around the chassis cage by 180 degrees and put a touch panel PC into the front of the chassis. So the image you see here is the visual impression of the load of the MicroTCA system. This system utilizes gigabit Ethernet with a lot of DSP power. In public transportation, Heiko mentioned that already. MicroTCA also made his pave in this particular case. This is a control system for a crossing system. So we are all aware, if you cross a crossing by red light, it might happen that a flash will hit you, or in fact that the traffic is controlled by how many cars are passing on a dedicated crossing. This is utilized by such a system which consists of a lot of independent processors, each of them running independently and controlling exactly one of the loops of the crossing. One of the major benefit was the fact that MicroTCA offers a fully redundant system, and that is utilized by this system. It offers redundant power supplies, but as well redundant MCHs. In medical applications, we found also MicroTCA is well adopted because we have a lot of customers using VME in the past, and nowadays they need to update their systems because there is a demand for higher bandwidth, higher speed, more processing power, and that is exactly where MicroTCA now gets into place. Most of the applications we had seen in the VME business in the past were utilizing gigabit Ethernet, which was not part of the original VME spec, but customers were using the front panel I/O of the CPU cards. And as such, we could easily convince customers to look into MicroTCA because MicroTCA comes with gigabit Ethernet in the backplane. And definitely that concludes my presentation. The physics community all over the place is utilizing MicroTCA, MicroTCA.4 in this particular case, for all their accelerator systems, the control systems for their accelerators. But also in the experiment hut, MicroTCA is the de facto standard. As said, that concludes my presentation. And I would like to hand over to Ivan.
Okay, yes. Thank you, Thomas. Thank you, Brandon. My name is Ivan Garcia. I'm President and CEO of Yoxos Technologies. Just a brief overview. We started our activities in 2007 and been active in fields like big science, military aerospace, transport, and industrial automation. And what we were offering, always FPGA-centric platforms based in open standards, mainly from Vita and PickMG. So since the beginning of our activities, VME was the reference standard despite its very old age. Don't forget that the VME next year will turn 45. So it's quite an impressive benchmark. But we see that the industry requirements are in constant evolution. So we internally run a survey among our customers in the different industries and domains, just to highlight what were the key factors or the key characteristics for the next embedded systems. And we found those 4 characteristics: an enhanced performance, higher reliability, a consolidated ecosystem, and that was also important, and finally, longer availability. Those are programs with quite important requirements in terms of availability for the future. So that was also important to be highlighted. So following those characteristics, we decided in 2016 to adopt MTCA for our new line of products. So why MTCA? As you see, it really fulfilled the 4 key characteristics. It was an emerging open standard. We had a growing community of both users and manufacturers. Then we found over the backplane the high-speed serial interfaces like PCI Express or multi-gigabit Ethernet. Also important to highlight on the backplane, synchronization. That was also very important. Then we had an improved modularity, like the use of micro RTMs to have additional space for additional electronics. And also high reliability, offering characteristics for redundancy, monitoring, and diagnostic. And finally, and that was also very important for us, it was that MicroTCA allowed us to keep the interoperability with other open standards. For example, the FPGA mezzanine cards, FMC. This standard we were using just to implement the analog front end in our VME platforms, and now it can also be used in our MicroTCA platforms. Of course, as soon as we started deploying the new products in MicroTCA, the first applications were more oriented to big science, especially in 2 groups. We had the real-time control and diagnostic systems for accelerators, especially for low-level RF control, BPMs, interlocks, and so on. And then we had this second one, applications for control systems in radio telescopes. But what we have seen, the trend in those last years, is that existing users in domains like military aerospace or transport, they start to assess the possibility of transitioning from VME to MicroTCA or from compact PCI to MicroTCA in order to take the key benefits we mentioned before. And last but not least, we also see that MicroTCA opened the door to new applications like quantum computing. So we see that for existing applications, we are there, and now there are also new opportunities. So we can say now that for our company and our community, MicroTCA is the new reference open standard. So that's all from my side. Thank you very much for listening.
Thanks, Ivan. Good stuff there. We are now into the Q&A portion of this session. We'll also invite back Doug Sandy when he has a moment. And as you can see, Tomas is with us now as well. So keep your questions coming. We'll get to as many of them as we can in the time that we have remaining. The big question I have here for you, Tomas, is you pointed out a ton of applications, a lot of them really cool, but the one that can't be overlooked obviously is what's happening in the physics community, where MicroTCA is essentially ubiquitous. So what are some of the capabilities or features of MicroTCA in those applications that, you know, translate well, you feel, into other verticals, you know, automation at large?
Yeah, glad you brought that up, Brandon. In fact, there are a lot of good features incorporated into the MicroTCA as it is. One of the things is MicroTCA, and that was one of the reasons why the physics guys has chosen MicroTCA to be their platform, is we have a wide variety of trigger and clocking signals available in the MicroTCA. So triggers and clocks is always crucial if you want to control sensors, if you want to control different machines and stuff like that. And simply because MicroTCA does offer these capabilities from scratch, that is something which really makes it ready to be used in other applications. We can easily daisy chain trigger and clocking signals from one chassis to another chassis. So basically, we are not limited.
Yeah. Yes. I will also add that for some new applications, for example, in radar, that we're asking for really scalability features. Synchronization over the backplane and triggering was really paramount, and we could answer all the requirements easily just using the standard and even adapting some features to fulfill all those requirements. So that was extremely important at this point.
And maybe for some listeners that are wondering what in the world is triggering and why is it important? Do I need it? So triggering is really important when you have to make things happen in a distributed system in a very, very low latency manner. So you can't wait for a message to be sent from one computer to another. That's too much delay or latency between them. Triggering is a solution that lets things happen much, much faster. So in all of these applications that were discussed, triggering was a very important element of it.
Thank you, Professor. One of the things that that was touched on here is that MicroTCA has been around for a while now, and obviously, as in Heiko's presentation, we saw some of the early interfaces that were used are now maybe not obsolete, but getting towards legacy. So what does the roadmap look like for MicroTCA technology, and how do you think, I will start with you, Tomas, how do you think that that's going to make it applicable more broadly in industry moving forward on the interface side?
Yeah, actually, when MicroTCA, as Heiko mentioned, when MicroTCA was brought up, we were basically talking about PCI Express Gen 1, Gen 2 was on the horizon. Somehow, when MicroTCA .4 was specified, PCI Express Gen 3 was already available, but it never made it into the spec. And that was one of the reasons why we had to we had to make MicroTCA ready for the future. And we are now in the working group, we are talking PCI Express Gen 4, Gen 5. That is definitely something which makes MicroTCA ready for the next decade, as Heiko mentioned. Also on the gigabit Ethernet, 1 gigabit Ethernet is basically something you can do some basic housekeeping with. But if you need some dedicated bandwidth on packet transport, this is way too slow. So that was one of the reasons why we needed to discuss 10 gigabit, 40 gigabit, and even 100 gigabit Ethernet to be laid out in the new spec. And all of a sudden, these new fabrics or these new speeds for fabrics, along with higher signal passes, PCI Express X8 passes or X16 passes has been introduced into MicroTCA, and that is something which really makes MicroTCA valid as a valid choice for customer who want to preserve his investment he did over the last decade, or if he wants to step into a matured and good ecosystem of different vendors providing you with open platform systems, then MicroTCA is without any choice.
That's great. Well, unfortunately, we're about out of time. But for those of you who had questions that we weren't able to get to, we'll make sure that one of our panelists follows up. I'd like to thank Heiko Corte of NAT, Tomas Holzapfel of PowerBridge Computer, and Ivan Garcia of Ixos for giving us a look at how MicroTCA is making inroads in industrial applications. And we'd like to thank you, the audience, for attending and contributing to the discussion. I've sent, again, a link to the subsequent final session for today in the chat to you. And if you're not able to access that after this session is ended, it will dump you out onto a landing page where you can go and re-enter into the Unlimited Design Freedom for Edge server session, which we will be beginning in just a moment. We'll see you over there shortly. Thank you, gentlemen, for your insights.
Thank you for having us.